Okay, so we're just past 2 p.m. Eastern time there, so I think we'll just get started. Everybody's just about logged in now. I'd like to welcome you all to the fourth webinar in our SOLAS for Missing Data Analysis webinar series. Thank you all for attending. Today we'll be talking about the predictive mean matching imputation method in SOLAS. My name is Andrew Grannell, Senior Statistician here at Statistical Solutions. And I'm here with my colleague, Eoghan Murphy, who's also a statistician here. And I suppose just before we get started, I'll go through the format here. If you want to ask questions, feel free to ask questions throughout the webinar at any time. Eoghan will be handling those questions. And I'll be also taking some on the mic here throughout the webinar. There's a little text box that you should have there in the GoToWebinar window, and you can write your questions through the text box there. If the window is too small, you can resize the window. You can make it full screen if you like, or you can zoom in and zoom out using the zoom options on the view panel. Okay, so we'll get started. So just an outline of what I'm going to talk about today. So I just want to, due to the feedback that we've been getting over the last 3 webinars in the series, I'm just going to have a quick short recap on some of the main concepts when approaching and applying missing data multiple imputation analysis. So I'm going to just do a quick defining missingness again, look at some missing data patterns, and just to run through the previous models covered. Today we're going to do the methodology on the predictive mean matching method. We're going to run through a quick work example and some post-imputation analysis in SOLAS, and we'll always have time for questions and comments throughout the webinar. As you can notice there on the top right-hand corner of the screen there, I've got a logo from the Irish Statistics Association, the Irish equivalent of the American Statistical Association, and they recently, just last week, had their annual Conference of Applied Statistics in Ireland. So we attended that, and it was great to attend. We met a lot of people in the Irish statistics community, and it was great to see the advancements of statistics and see what people are doing research in there. I just said I'd mention that, and also we're quite active in attending many conferences. And if you'd like to meet us at any time, let us know what conferences you're going to, and I'm sure if we're going to the same one, we'd love to meet up and have a chat. So. Just running through the concepts here then. What have we covered so far in this series? We've covered defining the various types of missingness. We've covered breaking up the data into the various missing data patterns. We've talked about the predictive model-based method, the Mahler-Novus distance matching method, the propensity score matching method. We've done some various pre-imputation plotting techniques that you can explore in the missing data in your data set. And we've also done some various examples of post-imputation analysis. Just doing a recap, so defining the different types of missingness, there are 3 main types of missingness. Missing completely at random, where the missingness in the data does not depend on any of the information collected in the study. So of all the information that you've gathered, the missingness cannot be attributed to any of the information that we have. A subset of this then is missing at random, where the missingness is dependent on the observed information collected in the study. So something that we've already collected can be used to explain the missingness. And finally, not missing at random is where the missingness depends on the unobserved data itself. When using multi-imputation, we like to assume missing at random, as it's quite hard to model the other 2 definitions of missingness. So I have a little caution wet floor sign there. There must be caution taken when you're defining this step and making your assumptions before you approach multi-imputation. Next thing is the missing data pattern process. So here I have a diagram of a data set with 100 variables and 100 cases. The blue cells here denote a missing data point and the white is observed. So we have a scattered pattern here of missing data. Now what we do here is we try and reorder or reorganize the rows and columns of this data set to cluster as much of the missing data together into one group as possible. Usually in real studies, not all the missing data will cluster together, so we have a separate group of unclustered missingness too. And this is displayed in this diagram that I've drawn here. So after we reorganize the rows, as you can see, the rows and the columns now have different numbers there because we've reordered the rows and columns. I've managed to cluster most of the missing data into the bottom right hand corner there and put all the missing data together. And we have also these various scattered, spurious data points that would not cluster with the missing data. These missing data points here, we call this pattern the non-monotone pattern because we couldn't put it into this cluster. And what we like to do is we like to impute these values first. So if you can imagine, after we impute these, we have a pretty much complete data set except for the bottom right hand corner. So then we like to have as much information as possible before we tackle this corner here. And then we systematically impute these values so that by imputing one value, we'll have more information before we impute the next value, and after imputing that value, we have even more information, and so on. So this bottom right-hand corner here then is referred to as the monotone pattern, the missingness that we could cluster together. So then we use, after we've imputed these values, we use this, what I'll call a complete data then, to maximize the information so that we can impute these values down here. Finally then, just to round off the recap section here, we've covered three different models for using employing multiple imputation. The first one we covered back in January was the predictive model-based method, and we used an ordinary least squares regression model for the continuous and ordinal variables, and we used a discriminant model for the nominal variables. We also talked about Mahalanobis distance matching and match, and this is where we compute the Mahalanobis distance from each missing case to every fully observed case based on some fixed covariates, and we can define donor pools based on the closest Mahalanobis cases to the missing ones. And then just last month in April, we talked about the propensity score matching method, where we fitted a logistic regression model to the observed data, and then the propensity score was calculated as the conditional missingness given the observed covariates. And again, I have a safety sign up here that we have many different models to tackle the different types of data that you have. So why we're all here today is to look at the predictive mean matching imputation methodology, and we actually particularly like this method because you're always imputing the actual real observed data. So I'll go through it here now. Again, I'm just going to go through it graphically because we have support documentation that you'll all get with the various equations and things, but I like to talk about the actual concept first before we dig into any equations. So just going through the concept of it here. I'm going to graph a covariate here, x1, versus our outcome variable y. So y is on the y-axis, and our covariate x1 is on the x-axis. These blue dots here represent observed data for both x1 and y, and the red circles here represent observed values for x1, but we don't have it observed for the outcome variable y. So what we do is we fit a linear regression model to the observed data, and then what we can do is we can plot the missing value for the outcome, but observed for the x1. We can map that up, and we can get a model value for that outcome, for the outcome matched to that covariate value. And this is where the predictive model-based method stops. You would take this, the value on the line, this model value, and you'd impute that value. What the predictive mean matching value does is, and I'll show you here, we're just going to zoom in on this. I have another diagram. We're going to zoom in on the old plot, and what we do is, so say we've mapped it to this point here on the line, we now project all the values, observed values around that point onto the line, and we take the closest points on that line, and we use those to create a donor pool to select from. So we match the closest observed values. We don't observe the model, or we don't impute the model value. We impute observed values. So once we've created our donor pool, how do we select from it? Well, there's various different types of ways you can select from the donor pool, or create the donor pool, sorry. You can create the donor pool from two main ways in SOLAS. You can take the closest cases, and in SOLAS, where the default is 10 here, so you can take the 10 closest cases, or you can take the top 10% closest cases. So that's how we create our donor pools. Now let's talk about the properties of predictive mean matching. As I said, we fit a linear regression model to the data, to the observed data. We also know that this model is quite robust to deviations from linearity, and there's a nice paper published by Schenker and Taylor in '96 on this topic. And predictive mean matching especially is quite robust to these deviations of linearity. So you don't always have to have perfectly linear data, a linear relationship. This method is quite robust to that. It's also robust to including irrelevant predictors or irrelevant covariates in the model. So if you have an irrelevant covariate that you might have just put in there out of interest, it's not going to mess up your model or mess up your imputations. Also, assuming the correct model and missing at random assumption, predictive mean matching can produce quite consistent estimates for the expected value of the outcome, as well as the covariance for X and Y. And finally, with the predictive mean matching properties, as it's a matching method, it requires overlap between the observed and the missing cases. So what do I mean by that? Again, I'm going to revert back to my nice diagram, and I'm going to show you here that here's the diagram I showed you earlier, where all the missing outcome values are within the observed values. What if you had a missing value that was lay outside that? Now, with the predictive model-based method, we could just project our regression line out and take a model value and impute that. But seeing as this is a matching method, we need to find matches for that value. And if there are no matches for that value, then we can't use this method. So that's what we mean by saying we need an overlap between the observed and the missing values. Great. So that's the methodology, the whole concept behind predictive mean matching, that method. Again, we're going to be sending out documentation after this webinar with the actual equations and the theoretical side of it. So I'm going to go through a quick work example now in SOLAS. So I'll close out of this. I'll open up SOLAS. So here's the SOLAS opening window. At this stage, most of you now are quite familiar with how SOLAS looks. The data set is in a spreadsheet format, quite similar to Excel or SPSS. You can open a new data set or a existing data set. There's a script language window where you can write your own script from scratch, or you can run a imputation or run a model, and SOLAS will generate the script for you, and you can open up that script window and alter it to your liking. And also there's quite extensive help functions here too. So I'm going to open up one of the sample data sets that come with SOLAS, and it's called MI trial, multiple imputation trial for a clinical trial situation. So here we have a data set. It's quite a small data set. We've got 11 variables and 50 cases, 50 patients, and what we have here is readings for or measurements for the symptom duration, patient age, and we've got two measurements here, measurement A and measurement B. both measured at baseline, 1 month after, 2 months after, and 3 months after baseline. As you can see here, there's quite an extensive amount of missing data in here. So the first thing we like to do is just to explore how the missing data looks. If we follow the progression from the slides earlier, we're gonna first do up a diagram of how the missing data looks. So we can just go to View and Missing Data Pattern. So we're going to try and break up the data into monotone and non-monotone. And how SOLAS works is a click and drop system where you can just pick up a variable and drop it into the box you require. We also have a use all function here. So if you click use all, now you can see here's something similar to what I had in the slides, where the blue represents missing value and the white represents an observed value. We have a list of all the variables that we're plotting here, and this is quite a large matrix of the 11 variables and the 50 cases on the rows. So firstly, what I'm going to do is I'm going to collapse this down into a more readable format. So we can collapse this table down. What we've done is we just collapse the rows onto each other. So now I know there's 39 out of the 50 cases are fully observed. I know there's 4 cases with this particular missing data pattern, and so on. So now what I want to do is I want to reorder the rows and reorder the columns. Reorder the columns, reorder the rows, so that I can put as much of the missing data into a clustered form. So here I'm going to go to View Monotone Pattern, where now the red represents the monotone, and this blue here, or light blue, represents the non-monotone missing data pattern. So as you can see here, we've managed to fit cluster as much of the missing data together as we possibly can, and this is the residual amount left over. So what SOLAS will do is it'll impute these values first to give us as much information as possible, and then we'll start imputing these one by one systematically to give us more information before we impute the next value, and so on. So that's a quick way of just exploring how the missing data looks in your data set. The next thing you might want to do is explore how the missing data exists in a relationship between two variables. So normally how we explore a relationship between two variables is we just do up a scatter plot. And we have a version of a scatter plot which we call a margin plot. And essentially this is a scatter plot with extra information given in the margins or the axes. So I'll show you a quick example here. I'm going to plot the measure A2 versus baseline measure for A. And we can see here that here's our typical scatter plot where the blue dots are observed values for both measure A0 and measure A2. And then the blue is line here is a box plot to give the distribution of the observed, and this box plot gives the distribution of the observed for A2. And then the red box plot here gives the distribution of these missing data points here highlighted in the bottom on the x-axis. So this can show us quickly and easily how the missing data is affecting a particular relationship between two variables. It's quite a useful feature. So I close out of that, and I'm going to do an imputation, a multiple imputation. So we'll go to Analyze Multiple Imputation, and we have our 5 different types here. Today we're doing the predictive mean matching. And I'm going to first define the linear regression model. I'm going to use symptom duration, age, and the baseline values as the fixed covariates, and then I'm going to use those values to impute the missing values for all the other measurements in the data set. We can also define how many imputed data sets we want to create. SOLAS does a maximum of 50, but just for display here, for an example, for illustration, I'm going to use 5 data sets. We can also go ahead and define how we want to impute the order of the non-monotone and monotone data, missing data. We can also go on, as I said before, there's different ways of defining the donor pools. I'm going to use the top, or the closest 10% observed cases. I'm going to use that option. And then we can also, there's several advanced options here, such as the seed option, where if you want to reproduce an imputation, you can just record the seed value, and every time you use the same seed, it'll redo the same imputation for you. So when you're ready, you can click OK, and it's going to generate 5 complete data sets for me. So it's quite a small data set, so it did that quite nicely for me. So I've got 5 new data sets now, and I've got all the missing values now have been filled in. So as you can see here as well, I've got 2 different types. I've got the red imputed data, and I've got these light blue imputed data. And this goes back to the missing data pattern that I showed earlier, where the red values are the monotone missing data pattern values that have been imputed, and the light blue here are the non-monotone missing values that have been imputed. And at the very bottom here, you can see the tab, dataset 1, dataset 2. So these are all 5 data sets complete and imputed. So now if we want to examine the same scatter plot again, but now with the imputed values, we can see here that the blue triangles are the observed values, and the red triangles here are the imputed values. And as I was on dataset 1, these are the imputed values for dataset 1. If I want to see the remaining, the complete imputed values for across all 5 datasets, I can just click Show Me All the Data Points, and it will overlay all 5 values on top of the one plot, and you can see it's quite representative. It's a nice handy feature, again, just to graphically examine the range or the distribution of the imputed values. Finally, I'm going to go through here just a quick post-imputation analysis, and I'm going to again run a multiple regression here, just to keep it easy. We're going to predict, let me see, measure B2. So when I select the outcome variable, up pops a regression window here, and I've got 2 sub-windows within the main window. And these windows are variables not in the model and variables in the model. Now if I go to model, I can get SOLAS to do the regression for me, a stepwise regression for me, and I want a step-by-step intervention. So I'm just going to click OK here. So it's telling me measure B3 is in first, measure B1, and also measure A3. It's interesting. So these three variables now are in the model for dataset 1, and it's interesting just the information given here. We've got the R-squared values, adjusted R-squared, and we also have the equation of the line here, where we got the intercept value, the coefficient for variable 1, coefficient for variable 2, and coefficient for variable 3. So we can repeat this again for the second data set. So again, we have variables not in the model and variables in the model. I want to do an automatic stepping. So again, measure B3, measure B1, and measure A3. So these variables again go into the model for this data set. The R-squared again now is quite similar. The R-squared for data set 1 was 85%. R-squared here is 89%, slightly higher. And I'll just try one more data set here just for the example. So again, same variables went into the model again, A3, B1, and B3. Also, just to note that this is a quite handy feature. If you want to force in or out a variable in or out of the model, you can just pick it up and drop it, and pick it and drop it. So if you want to put one in, you can just take it out of the variables not in the model and drop it in. Again, quite easy to use, quite time saving. So we also have you have a tab here for each data set and run a regression model on each data set. And we also have a combined tab at the end here to give you all the combined statistics. So we have the multiple correlation for this model. We have the mean coefficient value for each variable in the model and the standard error associated with that coefficient value. And we also are given the partial correlation for each variable not in the model. Also, what's quite nice is we can do quite a lot of diagnostics and diagnostic plotting, Cook's distance, various different metrics there to do your diagnostics on the regression models in SOLAS. So that was just a quick example of imputing using predictive mean matching and doing some quick post-imputation analysis both graphically and regression-wise there. So I'm just going to finish up with SOLAS there and go back to the presentation. So I just want to round off the webinar by saying that we've got 2 webinars left in this series. The next one in June, we're going to look at this combination method where we combine the propensity score matching, predictive mean matching, and the Mahalanobis distance matching methods in it to incorporate the best properties of each method to come up with quite a strong method there. Also then in July, we have a sensitivity analysis method where we feel this type of analysis goes hand in hand with multi-imputation, where you must stress test, I suppose is the word, to stress test your models and stress test the data once you've done the multi-imputations to check various variances and volatilities and so on. And also, I suppose the main conference that we've got coming up is in July in San Diego, which is the next JSM. We're very much so looking forward to that. And if anybody wants to meet us, we've got a booth there. You can come up and talk to us. We'd be delighted to meet everybody. So just to round it off, I'd like to thank everybody for attending today. I hope you all found it informative and useful. I'd like to leave some time now for questions and comments if anyone would like to start sending any in. Due to the volume that have attended here today and also the volume that has been attending over the last couple of months, it's quite hard to get to everybody's question during the session, but we try our best to follow up in a timely fashion with everybody's question. We really like to engage in discussion with people and also get people's views on it. You can contact me directly at andrew.grannell@statsol.ie. Our office number is given here. You can also find me on LinkedIn at linkedin.com/Andrew Grannell and on Twitter at AndrewStatsol. Again, I'm more than happy to take anyone's comments or questions at this time. Okay, so there's just a few questions coming through there that I'd just like to talk about. One was from earlier on in the presentation, just asking why do we cluster the missing data together by moving the rows and columns? Well, the order of the data in the data set doesn't really matter. It doesn't matter if case 51 is in position 51 or in position 102. So we can reorder the data and reorder the variables to put all as much of the missing data together as possible. And then what we do is we fill in the outlying ones using imputation methods. So it gives us as much information as possible before we start tackling the main body of the missingness, the main that bottom right-hand corner of the graph I was showing you. because that is, and then once we start filling in those, we use all the extra information. So if we impute the first value of that cluster, we use then that to help us impute the next value, and so on. So we're always gaining information as we're imputing. Another question there was, why did I create 5 data sets, and which one is the most accurate, or which one do I use? Well, again, theoretically, each data set should be the same. Obviously, there's a error associated with that because of the regression model and so on. But each characteristic-wise, each data set should be the same. So, as I showed you there, I ran the regression model in the post-imputation analysis. I ran the regression model on every data set, and then you looked at the combined results, and you look at the standard error associated with each covariate value, and you see how accurate the measurements are. In terms of nonlinearity, there's a question came in, how susceptible is this to nonlinearity? Again, just that paper by Schenker and Taylor, 1996. It goes through how susceptible it is, but this method is quite robust to nonlinearity. Again, you can just try it and see, and do some sensitivity analysis examining how volatile it is. So I suppose I'll round it off there because we're coming close up on the time there. So and I'm aware that everybody's got their own work to do. If you'd like to try out SOLAS, just if you're new to this imputation world, and if you'd like to try out running multiple imputation on your own data, because it's very easy to watch someone doing it, but trying to do it yourself is a different thing altogether. If you'd like to try it yourself, you can just take a no strings attached trial or something, and you can just test it out on your own data there. And I'm more than happy to help if you want to ask me any questions. Again, just email me or contact me through LinkedIn or something, and we'll be happy to have a discussion with you. So I'd just like to say again, thank you everyone for attending. It's great to see the numbers attending our webinars, and great to see the interest in multiple imputation and missing data analysis. I hope to see you all at the next webinar in June. So thank you again.